Good morning all. My name is Santhosh Kumar, Assistant Professor, Institute of Aeronautical Engineering. My subject is image processing. Today I am discussing about sharpening spatial filters. So what is sharpening spatial filters? Sharpening spatial filter is also known as smoothing. It is using to blurring the edges and reduce the noise less. So it is a derivative filter. And the purpose of the sharpening spatial filter is just the opposite to the smoothing spatial filter. And the main focus on the removal of blurring and highlight the edges. And it is based on the first and second order derivatives. So before going to this topic, already we know that these are the two types. Spatial domain are the two types. Smoothing spatial filter, sharpening spatial filter. Smoothing spatial filter, sharpening spatial filter. So in the previous session we discussed what is smoothing spatial filter. Today we are discussing about sharpening spatial filter. So sharpening spatial filter is also known as a derivative filter. The purpose of the sharpening spatial filter is just the opposite of the smoothing spatial filter, and the main focus of this is removal of blurring and highlight the edges. It is based on the second order and first order derivatives. So what is first order derivative? It must be zero in flat segment. It must be non-zero at the onset of a gray level and must be zero at non-zero Lang ramps. And first order derivative is a 1D is given by f dash equal to f of x plus 1 minus f of x. Okay, it is the equation for first derivative. So f dash means I am applying the Fourier transform. So the Fourier transform of function f, that is a f dash equal to f of x plus 1 minus f of x. Okay, so what is the use of first and second derivative? Okay, so we have to go for the noiseless and removing the blurrings. We need Fourier transforms for original image rectification. So first order and second order are the derivatives are for the spatial filtering. So what is the first order means? We are removing the blurrings and removing the noise. Okay, so first order derivative for must be zero at flat segments, must be non-zero at the onset of a gray level step, must be non-zero along ramps, and it is a derivative of 1D is given by f dash equal to f of x plus 1 minus f of x. So what is the second order derivative? It must be zero. So these are the conditions, and must be zero at the onset and end of a ramp, and must be zero along ramps, and second order derivative is a 2D given by f dash equal to f of x plus 1 plus f of x minus 1 minus 2 into f of x. So f double dash means Fourier transform of function. Okay, double Fourier transform. Okay, so f double dash equal to 2 times Fourier transforming equal to f of x plus 1 plus f of x minus 1 minus 2 into f of x. It is a second order derivative. And what are the common sharpening filters? So unsharp masking, high boost filtering, gradient first order derivative, and Laplacian, that is a second order derivative. These are the sharpening filters. Okay, so unsharp the masking. So what I'm using the mask is using in filtering. So mask is using in filtering. Unsharp masking means removing the blurrings or whatever, removing the noise. Okay, the mask is using. So unsharp masking is the sharpening filter, and high boost filtering, gradient first derivative, Laplacian second derivative. So what are the useful emphasizing fine details? The elements of the mask contain both the positive and negative weights. So what is a mask element? It is a sum to the 0. Okay, it is one example of 3 by 3. So middle point I'm taking as a 0. So remaining all I'm taking minus 1, 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 minus 1. Okay, it is a 8 table. So the emphasizing the fine details, the elements of the mask contain both positive and negative weights. Mask elements sum to be 0. And what are the examples? We are emphasizing the edges in an image. So what is the input image? See, here I'm taking some input levels with intensity values. So we are emphasizing the edges of the image. So the input I'm taking one example, that is the intensity levels. So when I'm converting the 1 by 9 means 1 by 3 square means 3 by 3 matrix. I'm taking 3 by 3. Why? Because 1 by 9 equal to 3 square. So it is a 3 by 3 matrix. So 3 by 3. So I'm applying this mask 3 by 3 mask to the input image. So what is the output image? What I'm expecting the output. So 1 by 9 of these intensity values of this one and 1 by 9 of second intensity values. Okay. So it is 0 and it is a less than 0. So these are the input images with applying the mask of 3 by 3. And it is one example of input image, and it is the input, it is the output. So what is output means? Sharpened image. Okay. Yeah, sharpening. Okay. Sharpening technique is applied. So sharpening spatial filter is the removing, adjusting the sharpenings. Adjusting the sharpenings. Okay. For better visualization, the original image is typically added to the sharpened image. Okay. So for better visualization, the original image is typically added to the sharpened image. Okay. It is the original image. For this original image, for the better visualization, we have added some sharpening technique to this image. Okay. The output is a sharpened image. And first obtain a sharp image by subtracting a smooth, that is low passed image from the original image. Okay. Suppose here I'm taking one logo, one text, that is a text minus text is equal to what is this one? Okay. To sharpening the image by subtracting a smooth, that is a low passed image from the original image. So what is the original image? From this original image I am removing the another one. So what is the final one? Okay. The contrast enhancement has been applied for better visualization. So it is another example. Image sharpening, emphasizing edges, but details are lost. So here one example of sharpening filters with unsharp masking and high boost filtering. Unsharp masking and high boost filtering. So image sharpening emphasizes edges, but details are lost. Add a weighted portion of G mask back to the original image when k equal to 1. This process is known as high unsharp masking. When k is less than 1, this process is known as high boost filtering. So here I am taking 3 conditions. Add a weighted portion of G mask back to the original image when k equal to 1. This process is known as high unsharp masking. When k less than 1 or k greater than 1, this process is known as high boost filtering. Okay, it is I am taking one image. So this image I am adding plus k is a technique operator. So I'm using one operator. So what is the output? Okay, this is the output image. Okay, input image with operator, that is the output image. So it is a high boost filtering. So when I'm going for the output, so it is the output, it is the operator. It is the input function. So high boost filtering example. So I'm taking one original signal. It is the input function. Okay. So it is a blurred signal. it is a figure B, and it is a unsharpening, and it is a sharpening. So there are 4 are there. First image is a input, that is a original. Second one is a blurred signal. The blurred means some noise is occurred, and unsharp masking. We are not sharpened this one. So what is the shape of this one? We are not sharpening means like this. Sharpened means we are going for like this. Okay, it is a flat line. It is a straight. So here illustration of the mechanics of the unsharp masking. First one is the original masking. B is a blurred signal with original shown dashboard references, and the third one CBT is a unsharp mask, and D1 is a sharpened signal obtained by adding C2A. Okay, it is one example of sharpening spatial filter with high boost filtering. It is another example. So it is a 2D example. It is a original one. It is a Gaussian smoothing, G mask, and unsharp masking when k equal to 1. High boost filtering when k is greater than 1. So there are how many conditions are there? I am taking one input condition. So for this input, I am applied as a Gaussian smoothing filter, then G mask applied, and unsharp masking with k equal to 1, and a high boost filtering k greater than 1 I am applied. Okay, here what is the figure A? So here figure is a original image, and B1 is a result of blurring with a Gaussian filter, and image C is a unsharp mask, and D is a result of using unsharp masking, and E is a result of using high boost filtering. So how many are there? Total input including input, total 5 are there. First one is a original, second one is a result of blurring with a Gaussian filter, C1 is a unsharp mask, D result of using unsharp masking, and the last one is a result of using high boost filtering. Okay. So what is the foundations of the sharpening filter? It is a Laplacian operator, and unsharp masking, and a high boost, and using the first order derivative for nonlinear imaging as a sharpening. It is a gradient. Okay, these are the 3 spatial foundation techniques are there. Laplacian operator, unsharp masking, and high boost filtering, and using first order derivative for nonlinear image sharpening. It is a gradient. So three types are there using in spatial filtering. So the first order derivative of a one-dimensional function f of x is the difference, and the second order derivative f of x is the difference. So what is the function of the first order derivative of one dimension? Dou f by dou x equal to f of x plus 1 minus f of x. It is the first derivative. Okay, so when I am going for the second order as f of x, dou square f by dou x square equal to f of x plus 1 plus f of x minus 1 minus 2 into f of x. It is also one dimension, but it is the second order filter. Okay, so there are first order and second order derivatives are using in sharpening spatial filter. The first order derivative is a one dimensional, that is f of x equal to dou f by dou x equal to f of x plus 1 minus f of x, and the second order is a dou square f by dou x square equal to f of x plus 1 plus f of x minus 1 minus 2 into f of x. And these are the some examples. Here the figure A and the figure B are there. So figure A is the of the first order second order derivatives of a one dimensional digital function representing a sectorization of a horizontal intensity profile. A and C are the data points adjusted by the designing of the lights. So here A and it is a B and it is a figure C. So in the figure A, I am taking x-axis as the intensity values and y-axis are the pixels. Okay. So when x-axis I am taking number of pixels and y-axis is the intensity. So I am taking intensity from 0 to 6 values. So when I am going for the increasing the pixels, so it is going to the this one, that is a intensity transition. It is going down, that is a ramp, and constant. When it is going to the upside, okay, it is a step. When I am going for the step upside, it is a step. When I am going for the downside, it is a ramp. So when these are the intensity values of this one, So first order derivative values, and these are the second order derivative values. Okay, so it is the intensity values, first order and second order. It is the output and it is the input value. Okay, when I'm using it is a mask or filter. So it is like this. So the second order isotropic derivative operator is the Laplacian for a function image f of x comma y equal to delta square f equal to dou square f by dou x square plus dou square f by dou y square. So here dou square f by dou x square equal to, already we know that f of x plus 1 comma y plus f of x minus 1 comma y minus 2 into f of x comma y. It is a two-dimensional function. It is also two-dimensional function. It is also two-dimensional function. Why? Because here I'm operator x comma y I'm using. Here x comma y I'm using two coordinators. But you can see here only one dimensional. Why? Because only one coordinator used. So the second order isotropic derivative operator is the Laplacian function image f of x comma y equal to delta square f equal to dou square f by dou x square plus dou square f by dou y square. So dou square f by dou x square equal to f of x plus 1 comma y plus f of x minus 1 comma y minus 2 into f of x comma y. So dou square f by dou y square equal to f of x comma y plus 1 plus f of x comma y minus 1 minus 2 into f of x comma y. So delta square f equal to f of x plus 1 comma y plus f of x minus 1 comma y plus f of x comma y plus 1 plus comma f of x comma y minus 1 minus 4 into f of x comma y. So it is a second order derivative isotropic derivative operator for the Laplacian function. So delta square equal to dou square f by dou x square plus dou square f by dou y square. So dou square f by dou x square equal to f of x plus 1 comma y plus f of x minus 1 comma y minus 2 into f of x minus y. So dou square f by dou y square equal to f of x comma y plus 1 plus f of x comma y minus 1 minus 2 into f of x comma y. Delta square f equal to f of x plus 1 comma y plus f of x minus 1 comma y plus f of x comma y plus 1 plus f of x comma y minus 1 minus 4 into f of x comma y. So it is a second order isotropic derivative operator using the Laplacian function. It is another example. I am taking here 4 3x3 matrices. First one is a mask filter used to implement. Here mask filter I am used. Okay, it is a filter B. So mask used to implement an extension of this equation that includes the diagonal term. Okay, it is also I'm using mask. But what is the implementing extension of this equation to includes the diagonal terms? Okay, and here C, another one is a D. So what is the C1 and D are the two other implementations of the Laplacian found frequently in practice. Okay, two other implementations of the Laplacian found frequently in practice. Okay, so the image sharpening in the way of using the Laplacian g of x comma y equal to f of x comma y plus c into delta square of f of x comma y, where f of x comma y is the input function and the g of x comma y is the output or sharpened image, and c equal to minus 1, or it is a constant if delta square of f of x comma y corresponding to the figure c equal to 1 if the either two filters are used. If I am using two filters, then c equal to 1. If I am c equal to 1 means f of x corresponding to the filter. Okay, So the image sharpened is a way of using the Laplacian g of x comma y equal to f of x comma y plus c of delta square of f of x comma y. Here another example, figure A is a blurred image. Figure A is the blurred image and B is the Laplacian without scaling. It is the image B, it is the image A and the C. So here C is the Laplacian with the scaling. And what is the D here? And the E function. So here C function already completed. D is the image sharpened. Sharpened image, and E is the after the result of this one using the mask. So it is the one example of sharpening spatial filter and unsharp masking and high boost filtering. So what is the unsharp masking and what are the high boost filterings? So first going for the unsharp masking. So the sharpening images consist of subtracting an unsharp, that is a smoothened version of an image from the original image. And the example is a printing and publishing the industry. So unsharp masking is the sharpened image consists of subtracting an unsharp or smoothened version of an image from the original image. And example, it is a printing and publishing the industry, that is a unsharp masking. And steps, what are the steps for this one? Blur the original image, subtracting the blurred image from the original, add the mask to the original. So these are the steps for sharp mask. Okay, what are the steps means? We can see again, blur the original image, subtracting the blurred image from the original, add the mask to the original. Let f dash of x comma y denotes the blurred image. Unsharp masking is g mask of x comma y equal to f of x comma y minus f dash of x comma y. The add a weighted portion of the mask back to the original, g of x comma y equal to f of x comma y plus k into g mask of x comma y, k greater than or equal to 0. So here I am taking unsharp masking, f dash of x comma y denotes the blurred image and unsharp masking. Okay, so f of x comma y is different and f dash of x comma y is a different. So here I am taking f dash x comma y is a So there are two problems are there in the original. F dash x comma equal to blurred image with unsharp masking. So what is the output? Output g of x comma y equal to f of x comma y minus f dash of x comma y. Then added a weighted portion of the mask back to the original. G of x comma y output equal to f of x comma y input with the constant value with the output mask of x comma y. Here k is greater than or equal to 0. So when k equal to greater than 0, the process is referred to as a high boost filtering. Okay. It is another example, unsharp masking of the demo condition. So it is the original image, figure A, and it is a blurred image, it is the unsharp image, it is a sharpening image. Okay. So input image, it is a blurred signal, unsharp mask, and sharpening image or sharpened signal. Here there are the original image, results of blurring with a Gaussian filter. First one is a original one input, and B1 as a blurry, and third one is a unsharp mask. So fourth one is a so last one is a output image with a high boost filter. When I'm calling it is a high boost, when k is greater than 1. So for function f of x comma y, the gradient of f at coordinates x comma y is defined as delta f equal to gradient of f equal to gx gy dou f by dou x dou f by dou y. So I'm taking the function f of x comma y, the gradient function f at coordinates x comma y is defined as delta f equal to gradient of f equal to gx gy dou f by dou x and dou f by dou y. These are the functions, and the magnitude of vector dou f denote as a capital M of x comma y. So here capital M of x comma y equal to magnitude of delta f equal to square root of gx square plus gy square. So the magnitude of vector delta f denotes as capital M of x comma y. So here M of x comma y equal to magnitude of delta f equal to square root of gx square plus gy square. So it is the image sharpening based on first order derivative. So it is another one, image sharpening based on the first order derivative dou delta f equal to function and denoted by m of x comma y. Here m of x comma y equal to magnitude of delta f equal to gx square plus gy square. Already we know that gx square plus gy square. So m of x comma y equal to gx plus gy, gx plus gy, m of x comma y equal to z8 minus z5 plus z6 minus z5. Okay. So the image sharpening based on first order derivative. What is the operator? Here I am using Robert cross gradient operator. What is the formula? M of x comma y equal to z9 minus z5 plus z8 minus z6. Next one is a Sobel operator. M of x comma y equal to z7 plus 2z8 plus z9 minus z1 plus 2z2 plus z3 plus z3 plus 2z6 plus z9 minus z1 plus 2z4 plus z7. I am using here 8 neighbor or 3 by 3, 8 adjacency. So another one is a image sharpening based on first order derivative. So here A, B, C, D, E. So here image A, the region of images with ZS intensity values, B to C, Robert cross gradient operator, D to E, Sobel operator. Already we know that Robert and Sobel operators. Here B and C. These are the Robert cross gradient operator. So here these I am taking as a so what is the reducement? All the mass coefficients are sum to 0 as expected as a derivative operator. So here another example of sharpening. First image and the second image. So here the first one is an optical image of contact lens note as deflects on the boundary at 4 and 5 o'clock, and Sobel gradient original image courtesy by Pets. Okay, okay, it is a Sobel. So it is a optical image. First one, optical image of a contact lens, node defects on the boundary at 4 and 5 o'clock. Second one is a Sobel gradient original image. Okay. So these are the list of references. So these are the sharpening spatial filters and its types. So already we discussed that one. So already we know that there are two types are there: smoothing spatial filter and sharpening spatial filter. So what is the smoothing? Already we discussed. Smoothing means okay. So what is the sharpening? It is also known as a derivative filter, and the purpose of the sharpening filter is just the opposite to the smoothing filter, and the main focus on this is the removal of blurrings and highlight the edges, and it is based on the first and second order derivatives. So what is the first order means? It must be 0 and must be non-zero. It must be non-zero along ramps, and the first order derivative is a f dash equal to f of x plus 1 minus f of x. Second order derivative is a must be 0 and must be 0 at onset and must be 0 along ramps. And what is the second order derivative? It is a 1D function, and take it 1D. So f double dash equal to f of x plus 1 plus f of x minus 1 minus 2 into f of x. What are the common sharpening filters? Unsharp masking, high boost filtering, gradient first derivative, and Laplacian is a second derivative. So what are the useful of emphasizing the details? The elements of the mask contain both positive and negative weights. Mask elements sum to 0. So here I am taking the mid one is a 0, surroundings are the minus 1. Okay, it is a 8 neighbor or 8 adjacency. I'm taking 3 by 3 matrix. So emphasizing edges in an image. Okay, input image with intensity values. So for this one, I'm applied mask. Input plus mask equal to output. So sharpening spatial filters, input image with sharpened output. So what are the what we are applying means I'm applying the sharpening technique to getting the sharpened edges. Okay, sharpening the edges. So it is a better visualization comparing to the original. So it is obtaining the sharpening. Okay, we are using subtracting method. Here I am using addition method. Input with operator, multiplication with second image with operator, that is the output image. So here I am using k equal to 1 and k greater than 1. Okay, when I am k greater than 1, it is a high boost filtering. It is a high boost filtering when k greater than 1. When k equal to 1, it is a high unsharp masking. High unsharp masking. It is a k equal to 1. It is a k greater than 1. These are the high boost filtering examples. First one is a original image. Second one is a blurred. Third one is a unsharp. And the final one is a sharp and signal. So this is another example of original image. The result of second one is a blurred image and the unsharp mask. Fourth one is a result of using unsharp. And the final one is a result of using high boost filtering. So what are the foundations of the sharpening filter? Is a Laplacian operator, unsharp masking, and high boost filtering using first order derivative for non-linear image sharpening. And the first order derivative of the function is dou f by dou x equal to f of x plus 1 minus f of x. And second order function is a dou square f by dou x square equal to f of x plus 1 plus f of x minus 1 minus 2 into f of x. Okay, it is one example of the ramp and step function. And it is a second derivative equation with a 2D. It is a sharpening spatial filter with a Laplacian operator. So image 1 is a filtered mask used to implement. Figure B is a mask used to implement an extension of this equation. And C and D, two other implementations of the Laplacian found frequently of practice. It is a Laplace operator of the smoothing and sharpening spatial filters. And it is the equation for Laplacian operation or with sharpening spatial filter. G of x comma y equal to f of x comma y plus c into delta square of f of x comma y. And it is some examples of figure A is a blot image, and B is a Laplacian without scaling, C image is a Laplacian with scaling, D image is a image using the mask, and the final one is the original image with adjusting the sharpenings. Okay, and it is a unsharp masking, and when high boosting it is a k greater than 1. It is the equation for unsharp. It is some images with unsharp masking. That is the figure A original blurred image, unsharp masking, and a sharpened signal. Okay, it is another example for unsharp masking with a high boost filtering. First one is the original one, and figure B is a result of blurring. Third one is a unsharp masking, and fourth one is a result of unsharping. Final one is a result of using high boost filtering. Okay, it is the equation. The magnitude function, robot, and Sobel operator. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.